A circuit that has resistors and capacitors is called an RC circuit. And so RC circuits are analyzed in very similar ways to RL circuits, so RL circuits where we have resistors and inductors. The main differences are that when we're dealing with capacitors, we should use IC is C dV dt, which is our equation that describes the dynamics of a capacitor. Typically, it will be easier to solve for voltage instead of current. So typically, it is easier to solve for capacitor voltage instead of current. So with inductors, we preferred to solve for current. And the reason for that is that in the differential equation that describes the dynamics, we have the derivative on the voltage term. So usually you would algebraically manipulate your equations so that you have the voltage and the derivative of voltage and then solve for that. And another key difference is the initial condition. The initial condition will be the capacitor voltage instead of the inductor current. So capacitors really care about the voltage, inductors really care about the current. So when we're solving RC circuits, it's usually the voltage which will be the key variable that we want to look at. So let's have a look at an example. So in this question, we have a capacitor, 0.5 microfarad capacitor here, and we have a switch. So at times less than 0, the switch is connected in this configuration. So basically the voltage source here is going to charge up this capacitor, and we need to analyze this circuit to figure out what the initial voltage on that capacitor is going to be. And then the switch will move over and connect through here. So basically we will have the energy that was stored in that capacitor is going to discharge through the rest of that circuit, and we're going to analyze that transient as the voltage is discharged out of that capacitor. So the statement from our question basically asks us to go and find a few things. So we're asked for the voltage on the capacitor, we're asked for voltage across that 240 kilo ohm resistor, we're asked for current labeled as I0, and also the total energy that gets dissipated in that 60 kilo ohm resistor. So let's go ahead and solve this question. So the first thing that we need to do is find the initial conditions. So remember, the initial conditions will be the voltage on the capacitor. So first, find the voltage on the capacitor for negative times, for t less than 0. And of course, we're talking about steady state conditions here. So the circuit at steady state looks like, remember, capacitors are open circuit to DC. So the circuit at steady state looks like this. We have a 100 volt source which goes through a resistor and then through that little switch and then to the capacitor, but we replace the capacitor with an open circuit. So replace cap with open circuit, because that's the steady state DC behavior of a capacitor. And then our question becomes, well, what is this initial voltage just before the switch flicks? So the voltage at time 0 minus being just before that critical time of 0. And this one's pretty easy, all right? There's obviously no current flowing and no current flowing means no voltage drop across the resistor. So therefore the voltage, we can just read it straight off. Sorry, this is V0 minus. So the initial voltage is just 100 volts, reading directly off the circuit. If this was more complicated, we may need to do some circuit analysis to solve for that voltage. So that was step one. Step two in this process is to draw the circuit for times greater than 0 and solve the transient dynamics. Okay, so I'm going to redraw my circuit. So this was my circuit here. I will just copy and paste it down here. And we're going to look at the case of t greater than 0. So that means the switch has kind of moved across into this position. So we can ignore the voltage source because that's now basically disconnected from the circuit. So all of this part is not relevant. We do need to keep the amount of capacitance there, so I'll just try that again. All of this part is not relevant, and we just have the circuit that you can see here. And we know the initial voltage on this capacitor here, so V of naught is going to be 100 volts. So by the way, the voltage on a capacitor can never change instantaneously. So if the voltage just before the switch moves is 100 volts, then the voltage just after that switch moves must be the same. It can never change instantaneously. That's true for capacitive voltages and also inductor currents. So those things can never change instantaneously. So we know that initial voltage, and now we need to analyze this circuit. So what I'm going to do is simplify this a little bit. I'm going to combine this parallel combination here so that I end up with something a little bit simpler, just so that I can calculate the circuit dynamics more easily. I don't really want to have to deal with simultaneous equations right now. So let's simplify the circuit. And so what we need to know is the equivalent resistance on the right hand side is, so it's this R equivalent is 240 kilo ohms in parallel with 60 kilo ohms, which is the product 240k times 60k divided by the sum. That's 240k plus 60k. And I'll just quickly calculate that. Bear with me, 240 times 60 divided 240 plus 60. It's 48 kilo ohms. So that leaves us with the following kind of simplified circuit. So I have the capacitor that was 0.5 microfarads, which runs through 32 kilo ohms, then this R equivalent of 48 kilo ohms, and that's it. That's all we have in our circuit. Labeling our voltages on here, we have the voltage on the capacitor is this one, and the voltage V0 is over here. And we don't have access to information about I0 anymore because we've simplified that part of the circuit, but we still have information about the two voltages, so we can solve for those and then work backwards to get I0. So analyzing this circuit, we need to get a circuit equation that describes its dynamics, and so here we have a loop, so I'm going to use Kirchhoff's voltage law around this loop. So if I start in the bottom left corner and then kind of proceed. Let me first actually label a current here. So I should have a current that's flowing in this loop. And actually, important point so that my positives and negative signs are all correct is if I want to use my normal capacitor equation, right, IC is C to V dt, that is true for voltages and currents that are defined according to conventional current. So from the perspective of that capacitor, I should have a current labeled that goes from positive to negative. So that's the way around that I should use, should label my currents. If I had labeled the current the other way, then I need to put a negative sign in my equation for the capacitor. So I'm just going to label it according to conventional current. So actually when I do KVL, I will go in the direction of this I that I've labeled here. So that will give me, from the bottom side of the circuit, I will have 48,000 times I plus 32,000 times I plus V. I'll write it V of t because it's time varying. It's the capacitor voltage, and that is equal to 0. So combining those coefficients, 48,000 plus 32,000 gives me 80,000. So that's 80,000 I plus V of t is equal to 0. Now at this point I need to eliminate one of these variables, so I will use I is C to V dt, and the capacitance here is 0.5 micro, so that's 0.5 by 10 to the minus 6 times dV dt, and I will substitute that into my equation above. So I have 80,000 times 0.5 by 10 to the minus 6 times dV dt plus V of t is equal to 0. Simplifying these numbers a little, so 80,000 times 0.5 by 10 to the minus 6, so that is 0.04 dV dt plus V of t is equal to 0. So we're nearly there. What I would like to do for my separation of variables is I would like to have a coefficient of 1 in the front of dV dt. So I'm going to divide both sides of this equation by 0.04. So 1 over 0.04 is 25. So I'm just going to get, I'm going to get dV dt plus 25 V of t is equal to 0. Okay, first order differential equation with constant coefficients, so we can solve this one by separation of variables. So let's bring the v to the other side, multiply everything by dt, so I will get dv is minus 25v dt, bring the v over to the other side, so that's 1 over v. So I have this, which is something I can integrate. So left-hand side gives me natural logarithm of v, right-hand side gives me negative 25t plus a constant of integration. I also would have a constant of integration from the left-hand side, but I'm just bundling both of those together. So I have just kind of lumping everything into this one arbitrary constant. Solving for voltage, I take the exponential of both sides and bringing my arbitrary constant to the front of that exponential, giving it a new name. So that's, I'm going to call it A. So e to the minus 25t is my solution. I need to use my initial condition, so use the initial condition, IC. The initial condition was that the voltage at time 0 is 100 volts. So V of 0 equals 100. So I sub in T of 0 and I sub in V of 100. And so therefore 100 equals A e to the 0, which is just A. So therefore our final solution for voltage, for the voltage on the capacitor, is 100 e to the negative 25t. All right, let's go back and look at our circuit. So at this moment we have solved for the voltage here on the capacitor. We would like to know what is the voltage on this resistor here, so this V0. I can use my simplified circuit and just use a voltage divider. So let me just copy this one down so you can see what I'm doing, and we'll solve for that one. So this was my final answer for the voltage on the capacitor. Then to find what they call V0 of t, use voltage division. Use voltage division. So V0 of t will be V of t multiplied by 48k divide 32k plus 48k. So we can simplify these numbers. So 48 divide 32 plus 48, 0.6. So it is 0.6 times V of t, and we sub in what we know about V of t. That's this equation here. So 0.6 times 100 is just going to give me 60. So the answer will be 60 e to the negative 25t. Now we also were asked to solve for the current here, I0, that flows down this 60 kilo ohm branch. And this one is straightforward because we now know the voltage. So given that I know the voltage here, I also know the voltage on this branch. They're connected by the same nodes. So let's just copy that circuit so you can see what I'm doing, and I'll just use Ohm's law to calculate that one. So I'll just underline this was my final answer for V0. Then to find I0, use Ohm's law. So I0 is going to be V0 over 60,000. So V0 was 60 e to the negative 25t divided by 60,000. So that will just give me 1 over 1,000 e to the negative 25t. And that will have units of amps. I should label my units here. This one has units of volts. This one has also units of volts. Okay, the final thing that our question asked was the total energy that is dissipated in that 60 kilo ohm resistor. So that's the final thing to calculate. To find the total energy dissipated in the 60 kilo ohm resistor. First, find the power. So the few ways we can do this, but basically if we know the current and we know the resistance, then we have that power is I squared R. So I we just calculated, so that one is 1 over 1,000 e to the negative 25t, so it's all of that squared, multiplied by the resistance is 60 kilo ohms, so 60,000. And the answer for this, just bringing all of our numbers together, so 1 divide 1,000 squared times 60,000 is 0.06. And then on the exponential, the squared is going to multiply by the exponent, so that will give me negative 50t as the power. So this is like instantaneous power, but I'm asked for total energy. So the energy is going to be the integral over all times of this instantaneous power. So that's power with respect to time. So that is integral 0.06 e to the negative 50t dt. And to evaluate that, I will get 0.06 divided by negative 50 e to the negative 50t, and that is taken over my limits of integration. So I will have 0.06, that's a negative, divide 50, and then subbing in my limits, I will have for infinity, e to the minus infinity will give me 0. Subbing in 0 will give me 1. So the total energy that I will end up with, 0.06 divided by 50 is 0.0012 joules of energy. We could write that perhaps a little bit more friendly way, 1.2 millijoules of energy there. And so that's the answer to this question. So to recap our problem-solving strategy, basically the important steps of analysis. So the first thing that we have to do is find the initial conditions, which for a capacitor will be its voltage. Then we need to analyze the circuit in the transient configuration, analyze the circuit and get some equation that describes the circuit dynamics. And then we use our dynamics of a capacitor to turn that into a differential equation and then solve that differential equation.